Okay, cosets. So let H be a subset of a group G. So H is a subset of G. I'm not saying that H is a subgroup of G necessarily. It might be. It might not be. I'm not committing one way or the other just yet. Then you can define AH. This is the set AH such that H is an element of H. And you can define the set HA, which is HA such that little h is an element of H. AH is called the left coset, which contains A. Well, that seems to beg a, I mean, wait a minute. Who says it contains A? If H is in a subgroup, it doesn't necessarily contain A. I wouldn't say that. So let's just say this is the left coset with representative A. This is the right coset. It's a right coset. And to be more specific, it's a left H coset. This is a right H coset. Again, with representative A. All right. Now, I'm assuming a multiplicative group structure, right? What would the cosets look like if we were dealing with an additive group? Yeah, A plus H or H plus A, right? And if we were dealing with that, those would be equal too, right? Because, well, assuming that the additive group is abelian, and we do, right? Okay, so a little bit more notation here. We let the order, well, this vertical bar AH, that's the number of elements in the set AH, right? And likewise, the order of HA is the number in elements in HA. All right, so let's calculate a few of these. Not necessarily. Oh, A is an element of G. Yeah. All right, so excuse me. Let's do a calculation here. I'll follow the book. I like his example pretty well. He looks at G equal to the symmetric group on 3 letters, S3, right? And he looks at H equal to, maybe we can choose it to be whatever. I'll follow his example. Uses 1 and 1, 3. All right. So let's work it out. What's 1H is just what? So that's just H again, right? Let's see here. If we calculate, but by the way, it's also equal to what? Because if you multiply the elements in H by 1, 3, you get 1, 3, and then 1, 3 squared is the identity again, right? Because the transposition is order 2. Now if I look at, say, 1, 2 on H, well, that's going to be 1, 2, acting on 1 just give you 1, 2 again, right? And then 1, 2, 1, 3. which is what? This is actually what? 1, 1, 3, 2, right? Let's see here. And you can prove that this is equal to 1, 3, 2 acting on H, in part because 1, 3, 2 times 1, 3 is what? Start out with 1. 1 goes to 3. 3 goes to 2. 2 goes nowhere. 2 goes back to 1. 3 is fixed. Right? So, if you look at 1, 3, 2H, right, which would be 1, 3, 2, 1, 3, 2 acting on 1, 3, multiply 1, 3, well, this is exactly 1, 2 again. So you can see that this set and that set are the same. All right? Anything else we can calculate? Let's see here. How about 1, 3? Oh, we already got 1, 3. 2, 3? Yeah, we can do 2, 3. What's 2, 3 acting on H? What's 2, 3 times 1, 3? Let's see here. 1 goes to what? 3. 3 goes to 2. And then where's 2 go? 3. All right. And a short calculation will show that this is also 1, 2, 3 acting on H. Is there anything left? 1, 1, 2, 1, 3, 2. I mean, S3 is what? See here, 1, 2, 3, 4, 5. This is getting old. 6 elements. So that's everything. We've calculated all the cosets of H here. Right? Anything you see in particular from this pattern? I mean, what's special about this H that I didn't commit to in my definition of coset? I would point out to you that H is a subgroup of S3, right? In fact, it's a cyclic subgroup. H is the cyclic subgroup generated by 1, 3. Right? And we have a theorem, right? First of many theorems from today, but theorem, if H is a subgroup of G, then A is an element of AH, and A is an element of HA. How we can prove this theorem? I think the answer is with our eyes closed. Let's see your proof. This one's easy. Observe that A is equal to A times E, right? And E is an element of H because we're assuming H is a subgroup of G, right? Therefore, A equals to AE is an element of AH. Likewise, A is equal to E times A is an element of HA. Okay? But if I was to calculate cosets where it wasn't a subgroup, there really is no guarantee that the representative is in the coset, is there? Because you might multiply everything away from that element. You may never come back to A. All right. Let's work another example. Actually, I'm going to state a theorem rather than an example. Theorem. So basically here it is. I think I want to let Yeah, H be a subgroup. Let H be a subgroup of G, all right? And A and B be elements of the group G. Then we have a few things. One, let me see here. We actually have already, this is his lemma. I'm calling it a theorem. This is lemma on page 135, but all right, so here we go. Oh, should have just tore this page out, but I can't tear pages out of Galean. It hurts me. So, calculus book is different. This is not a calculus book. This is more of a work of art. It's not a grungy tool. It's, you know. All right, so AH is equal to H if and only if A is an element of H. 2, either AH is equal to BH or AH is intersect BH is the empty set. So they're disjoint or they're the same. 3, AH is equal to BH. This 3 is a big one. If and only if, calculationally, this is huge. A inverse B, huge, is an element of H. 4, my numbering's off by 1, by the way. The order of AH is equal to the order of BH. 6, 5, his numbering. My numbering is 1 off his. 5, AH is equal to HA if and only if H is equal to AH, A inverse. And finally, 6, AH is a subgroup of G if and only if A is an element of H. 6 seems unnecessary, but whatever. All right. All right, these are important. Let's try to prove them. Let's see here. 1, if we do the forward direction, right, suppose AH is equal to H, right? Note, I think that's almost the theorem we already have, isn't it? E is an element of H, right? Thus, A times E, which is equal to A, is an element of AH, right? But that's equal to H, so therefore A is an element of H. What about the converse direction for that one? Suppose A is an element of H. I want to prove that AH is equal to H, right? Let X be an element of AH, right? And observe that X is equal to what? X has to be equal to A times little h for some h in H, right? By definition of the coset. I'm trying to prove that X is an element of H as well, right? Oh, why is X an element of H? Thus, X is formed by product of what? X in H, right? I mean, excuse me, by A, which is in H, right? And H, which is in H. And H is a subgroup, right? Therefore, X equals to AH is an element of H. But what did I just do? I just showed that an arbitrary element of AH is in the subgroup, right? So I suppose that shows that H is a subset of AH, right? Now to go the other direction, what should I do? It's almost the same stupid argument. Let's let Y be an element of AH, right? What, I already did that? I already did that. Yeah, I'm sorry. All this unnecessary stair running. Let Y be an H, and I want to show that Y is an AH, right? Oh, you guys, don't let me... Look, is this right? No, what have I just proved? Thank you. If you see something, say something, you know? Let's see here. So then what? I'm trying to show that this is an AH, right? Y is equal to A inverse H, A inverse Y, right? Which is an element of AH. How do I know that this is an H, right? Let me just say it's an H. Why is A inverse Y an H? Y is an H. A is an H, so A inverse is an H. H is a subgroup. So Y is equal to the product of A with something in H. Therefore, it's in the coset AH. Hence, H is a subset of AH, right? So therefore, H is equal to AH. Again, this presupposes what? Right? A is an element of H. Let's look at 2. Let's see here. How are we going to prove 2? Let's see here. Suppose AH intersect BH is not empty, right? What do we want to show? If we can show that in the case that the intersection is not empty, they're equal, then this proves 2, right? Does that seem logical to you? Okay. So if this is not empty, there exists what? Like X, an element of the intersection, right? Which means it's in both things, right? Right? What does that mean then? There have to exist, say, H1 and H2 in H, such that what? X on the one hand is AH1, but X on the other hand is BH2. So these are related, right? What's to say about the relation of A and B? Let's see here. B is equal to what? B is equal to X H2 inverse, right? But what else? We can rewrite that again. That's what? That's A H1 H2 inverse. Aha! sorry, that's an element of AH, right? Because H1, H2 inverse is an element of H because H is a subgroup, right? So what do we have? B is an element of AH. What's that say? You say that says, oh, you think you can use that to prove that BH is a subset of AH? I suppose we could do that. I feel like there's a oh, never mind. I was thinking I could use 1 for 2, but I'm wrong. Yeah, you guys got the right idea. If B is in there, let's see if I can do this. Well, I mean, this is true, but let me just kind of, since you're making me go down that path, let me just, we have this, right? So let's say let Y be an element of BH, right? Then Y is equal to B times H3, right? I shouldn't really have erased what I just got. I'm going to try to rewrite B as A, right? So B is equal to, I shouldn't have erased that, I'm an idiot. XH2 inverse, right? So I'm just solving X equals to B H2 for B, right? But we can also do what? We can take that X and rewrite it as AH1. Okay, so now we've got A times the product of things in H, right? Which shows what? This is an element of AH, right? So what does this give us? Thus, Y is an element of AH, which implies that BH is a subset of AH. And I'm just going to say similarly, you can show AH is a subset of BH. Therefore, AH is equal to BH, and that completes the proof of 2. Right? I mean, there's really no distinction between A and B here. If you can make the argument go one way for A, you can make it go the other way for B, right? This statement is symmetrical as A and B appear. So if I can prove it for A, I can prove it for B. So that similarly is really not much of a leap. Okay? Let's move on to 3. Who is calling me? Quiet. He's not even actually calling me. Dr. Mavinga, who used to work here, has a phone, and it just calls me from time to time. It's not significant. I know, because I picked it up, and there's about a 1 in 10 chance it's actually him talking to me. Let's see here. I do welcome his calls, though. Let's see here. We have no one here who understands topology as deeply as he did. It's unfortunate. Okay, anyway, where was I? 3, right? So we want to show that AH equals to BH if and only if. And operationally, this is how we check equality of cosets, guys. Did I say AB? A inverse B? Yeah, A inverse B is element H. Before I go on with the proof, it's worth noting in the additive case, what's this look like? In the additive case, this criteria looks like A plus H is equal to B plus H if and only if what? If and only if, I guess it would look like minus A plus B But you could rewrite it as B minus A is an element of H. Okay. Okay. Just side comment. Okay, so the proof. Suppose AH is equal to BH, right? Thus, excuse me, A is an element of course, A is an element of AH by our earlier work, right? So that means that A is an element of BH, right? Which implies that there exists H in H such that what? A is equal to BH. Consequently, what? H is equal to AB inverse, right? Or, if you like, H inverse is equal to B, shnikes. Thus, AB inverse is an element of H. Well, I didn't prove what I wanted to prove, but there's something that's true. All right. What should I have done? How should I have, if I had chose a different path, how would I have got what we wanted immediately? What if instead I had said, thus, B is an element of AH, right? Which implies that there exists H2 in H such that B is equal to AH2. Thus, consequently, H2 is equal to A inverse B, right? Is an element of H. Yep.
So do you prefer what you wrote in red in this proof?
Well, what's in black doesn't prove the assertion, so it's kind of not so useful. But it's true. So I hate to erase it. I mean, we discovered something else that's true. It's kind of nice, but yeah, it's not what I was after. Sorry, poor planning on my part. How about the converse direction? Yeah, what's in red is the proof. What's in black is me wasting your time. Let's see here. Sorry about that. Suppose that A inverse B is an element of H, right? I'm just going to do I want to prove the equality of those two cosets. Maybe I can use two. Either they're the same or they're disjoint, right? So what's this say? This implies that A inverse B is equal to H for some H in H, right? That says what? That says thus what? AH is equal to B, right? Now B is an element of BH, right? We know that from our earlier work. And what does this say? This says that AH is also an element of BH, right? But what does that say? But AH is also an element of what? Thus, B is an element of AH intersect BH, right? Which is non-empty. So by 2, we have that AH is equal to BH. Okay. I probably should try to prove 4. How can we prove that the order of AH is equal to the order of BH. I mean, it's true in our example, right? 2, 2, 2, 2, 2, L2s, right? Before I get carried into this, though, let me check on time. We don't have much time. I may leave this to Galion. 2:50? Oh, I better go on. Golly. Actually, I can prove this pretty fast. Here, check it out. So we just define phi, a mapping from AH to BH by what? Typical thing in here has the form what? AX, right? So you map it to BX. And it's not hard to see that this is a one-to-one mapping. Right? So it says that the order of those sets has to match. Right? One element goes to one element. So that's essentially the proof. That brings us to Lagrange's theorem. And here it is. If G is a finite group, all right, if G is a finite group and H is a subgroup of G, then the order of H divides the order of G. All right. Moreover, the number of distinct left or right cosets, I'm just going to state it for distinct here, but the theorem also works for right cosets, is simply the order of G divided by the order of H. So first of all, I'd point out that this theorem is true for my example, right? The order of H was 2, and we found in this group of order 6, S3, right? 3 divided by 2 is 6 divided by 2, rather, is 3, right? And that was the number of cosets we had there. There are 3 of them. So here's the proof. And this is one of my absolute favorite proofs from this course. It's beautifully simple. So what you do is just say, well, let G be formed by the disjoint union of the cosets. So like H1 union A2H union da-da-da union AKH, where A1, A2 da-da-da AK distinct. More to the point, really, the A1H and A1, let's say AIH intersect A sub J H is equal to the empty set for I not equal to J. Why can I do that? How do I know that? I know every element in G fits into some coset, right? You pick an element of G, it's in that element times H, right? Because A is in AH. So every element of G is in at least one coset, right? But the cosets, right? We can also, we know by 2 here, either the cosets are equal or they're disjoint, right? So every element of G has to fit into just one of these cosets, right? You can have different labels for a given coset, right? Like here I can either say it's coset with representative 1, 3, or it's the coset with representative 1, or it's the coset with representative 1, 2, or it's the coset with representative 1, 3, 2. You got choices. But there's just one coset which contains the cycle 1, 2. It's this one, right? So this is you're writing G as a union of these disjoint sets, right? So what's the order of G equal to? Also, we know what? By this number 4, we know that the order of AIH is equal to the order of AJH, right? There's one of these. I guess without loss of generality, we can suppose that A1 is equal to E, right? If I do that, what's that make the first thing here? Just H itself, right? Just for the sake of making the proof more understandable, let's suppose the first thing there is the subgroup itself, all right? So these are equal, but of course those are also equal to the size of H, right? So counting, the order of G, right, is equal to the order of H plus the order of A2H plus plus the order of AKH, right? But this is just what? This is just K times the order of H. So what's that say? That says that H, the order of H, divides the order of G. Right? In other words, the order of G is a multiple of the order of the subgroup. I hope you appreciate how easy that argument is. Right? I personally, I love this argument. And you know, if I had my druthers, I would prove this before we do cyclic groups. Because you could use this to prove some of the things we did in cyclic groups much easier. You know, nothing we did in cyclic groups is that hard, fine. Now, this has a name. This K is called the index. Let me make sure I get the right number. So, where is this stupid thing? Come on, out with it, you stupid book. He denotes it. I think, make sure I got that in the right order there. Yeah. So basically, Lagrange's theorem can be restated. The index of G by H is G divided by H, the order of G divided by the order of H. Finite group, though, okay? Right. Now, I will say this. There's still something to be said here in the infinite case, right? Like, I can't do counting, but the cosets still give you some sort of disjoint. They give you a partitioning of the group into cosets, right? There's still that in the infinite case, even if there's not this counting. So that's significant. Let's see here. Corollary. A group of prime order is cyclic. All right, so here's the proof. Suppose G has prime order. Right? Let A be an element of the group. A not equal to the identity. What can you use? What can you do with A? Well, you can create the cyclic subgroup generated by A, right? So the cyclic subgroup by A that is a subgroup, right? Its order has to divide the order of the group, right? Which implies what? The order of A is either equal to 1, or the order of the subgroup generated by A is equal to P, because those are the only divisors of a prime. By definition of prime, right? But the order of A is not 1, because we assume that A was not E, right? So the order of A has to be P, which is to say what? It generates G. So groups of prime order are cyclic. Cool. So if you give me a group of order 17, it's cyclic. That is something we did not have before, and it was not that hard to get, was it? When we had that. So this concept of cosets already paying dividends big time. It will continue to do this as we go on. You're going to see it's a very, very powerful concept. I'll shut up here. My time is up.